Hi everyone. In this video, I will show how to calculate the current in a simple diode circuit using the ideal diode. This is the simplest method and even can be done without using pen and paper. It is used when we want to have a rough estimate of the current and a precise value is not needed. This is a simple diode circuit. In fact, most diode circuits can be simplified to this circuit. Let's first see what is the definition of an ideal diode and how is its characteristics. An ideal diode can conduct current only in one direction, and no current can go to the opposite direction. If the voltage across the diode is negative, no current goes through the diode, or the current is zero. It is said the diode is in reverse bias. It can be modeled as an open circuit or an open switch. When the current goes through the diode, the voltage across it is zero. This is like a short circuit or closed switch, and it is said the diode is in forward bias. For comparison, the characteristics of a real diode are shown here. In reverse bias, the ideal diode has a very good match with the real diode because it has the reverse saturation current, which is negligible and usually is assumed zero. At forward bias, you can see more difference. The real diode has a voltage of about 0.6 or 0.7 volts, but the voltage of the ideal diode is defined as zero. I will talk about this difference later in this video. Now let's calculate the current in this circuit. First, we need to find out if the diode is in forward bias or in reverse bias. The positive side of the battery is connected to the anode of the diode, and the cathode is connected to the negative side of the battery through the resistor R. Therefore, the current goes from the positive side to the negative side, and it is in direction of anode to cathode, and the diode is in forward bias. The arrow shape of the diode shows the direction that the diode conducts the current. To calculate the current, we simply replace the diode with its model or equivalent circuit in forward bias, which is a short circuit. Then we can write a KVL in this loop. We have V equals to R times I and equal to R times ID. The current in the loop is the current in the diode. From here, we can calculate ID equal to V divided by R, and if we put the numerical values, 5 volts divided by 2 kilo ohm equals to 2.5 milliamps. Remember that if you use the value of resistor with unit of kilo ohm, the current is found in milliamps. Here I have drawn the equivalent circuit and was writing a KVL equation only for explanation and for clarification. We really don't need to do that. By looking at the circuit, we can even have a mental calculations. 5 volts divided by 2 kilo ohms is 2.5 milliamps. What about the voltage across the diode? It is a short circuit, and short circuit by definition doesn't hold any voltage, or as the ideal diode is defined, when it is in forward bias, its voltage is 0. So we can write VD, or the voltage across the diode, equals to 0 volts. When we use the ideal diode model, it is when we want to have a rough calculation and the precise value of the current is not very important. The method can be quite accurate if the applied voltage is very large, much larger than the forward voltage of a real diode, which is usually 0.6 to 0.7 volts. For example, if the voltage is 100 volts, the current is calculated as 50 milliamps. The precise value is around 49.7 milliamps, and the difference is about 0.6% or less than 1%. For a voltage of 10 volts, the calculated current is 5 milliamps, and the precise value is 4.7 milliamps, about 6% different, still good. But what about if the applied voltage is 1 volt? Using the ideal diode, we calculate the current equal to 0.5 milliamp. The precise value is 0.2 milliamp. A massive error, more than 2 times. So we should not use the ideal diode model when the applied voltage is very small. What about the current when the diode is in reverse bias? In this figure, I have changed the direction of the diode, so the cathode voltage is more positive than anode voltage. Instead of changing the diode direction, we can change the polarity of the battery, negative on top and positive at the bottom. It would be the same. To calculate the current, actually we don't need to do anything to calculate the current, because by definition, the ideal diode in reverse bias has a current of 0. So the current is 0. But if you want, you can throw the equivalent circuit of the diode in reverse which is an open circuit, and hence the current is 0. It is important that the standard notation of the diode voltage is the voltage of anode in respect of the cathode, and the standard notation of the diode current is from anode to cathode. If the diode is in reverse bias, these values will be negative. So here, I actually is equal to minus ID, but because it's 0, it doesn't matter. What about the voltage across the diode? we can write a KVL equation in the loop. If we start from the left, V equals to minus VD plus R times I. And we know that the current is 0. So this is equal to minus VD plus R times 0. And from that, we can find VD equal to minus V and equal to minus 5 volts. This is very obvious because there is no current in the circuit, there is no voltage drop across the resistor, and all the applied voltage appears across the diode. Thanks for watching.